25 years, also written and lectured on the history of science, especially ancient Indian mathematics. He received the first Satish C. Bhatnagar Award in the history of mathematics of the Indian Mathematical Society. And he's been teaching the history of mathematics and science at the Ramakrishna Mission Institute of Culture in Kolkata, and written serially on mathematics in India for the journal Bhavana. Today he'll be talking about algebraic insights and algorithms and innovations of Indian mathematics.
So I thank the organizers for the opportunity to share some of the developments, and also for agreeing to my request to change the title of the talk. So the title that was suggested, because this is relevant to the thing, was about algorithms, computations, and innovations in Indian mathematics. And what I felt is that there is some kind of partition. This belongs to arithmetic, this belongs to algebra, this belongs to geometry, and so on. And the interconnections get lost. So I requested for this change of title, Algebraic Insights. That is, when you look at even something like arithmetic, read between the lines, as I say, that about the algebra. Now, in the introduction, it was mentioned that I work in affine algebraic geometry, and one of the pioneers in affine algebraic geometry in modern time is Sriram Abhyankar, one of the gigantic mathematicians of modern time. And he has a poem, mathematical poem, which starts with polynomials and power series, may they forever rule the world. So, point is that polynomials and power series are at the heart of modern algebra and algebraic geometry. Now, where do we find the algebra of polynomials? In India, we find it as early as in Brahmagupta in 628, and power series we find in Madhavacharya. Now, polynomial is not my topic. My topic is decimal system. So decimal system is an innovation. So it comes under the suggested title. But look at the algebraic. So I don't have to talk about the greatness of the decimal system. Much has been said about it. But look at the algebraic aspect of the decimal system. Think of a polynomial of degree n. It is represented as an x to the power n plus an minus 1 x to the power n minus 1 plus dot dot plus a1x plus a naught. That's one way of representing the polynomial. And in this representation, you need not write the coefficient if it is 0. But when polynomial is being introduced formally, those who have studied, algebra formally in college level would have known that this is also represented as a tuple, an n minus 1 dot dot a2 a1 0, and then rules of addition and multiplication are defined accordingly. And in this case, 0 has to be put as an entry if any coefficient is 0. So if you write in terms of x, you don't have to write 0, but in the tuple form, you have to write 0. For example, 2x cubed plus x squared plus 7 is a polynomial, but it can also be written as 2107. Now, just think of decimal representation. A number is expressed in decimal system as, orally as, and that goes back to the Vedic time, 2107. It's almost like 2x cubed plus x squared plus 7. But the more common decimal notation, that is 2107. Do you see the similarity with the polynomial and the decimal notation? So, decimal place value system is a 10-adic polynomial expansion. Now, what you may feel is that it is putting that once polynomials have come up, it is, seeing decimals, seeing polynomial in decimal is a bit too much. But that is not the case. Look at it historically. Newton is on record. So, Brahmagupta started polynomials in India, and in Europe it was given a big fillip by Newton. And what does Newton say in his own language? Since the operations of, so you remember that Newton's time is 17th century, and that is the time just before Newton, decimal system had finally got standardized in Europe. Decimal system and the arithmetic based on decimal system. Since the operations of computing in numbers and with variables are closely similar, I was amazed that it has occurred to no one to fit the doctrine recently established for decimal numbers in similar fashion to variables, especially since the way is then open to more striking consequences. For since this doctrine in species has the same relationship to algebra that the doctrine in decimal numbers has to common arithmetic, its operations of addition, subtraction, multiplication, division, and the root extraction may be easily learned from the latters. So what is Newton saying? That once you have this new system of arithmetic, the Indian system of arithmetic based on decimal system, why are you not copying it? And you get this algebra of polynomials. And more recently, even in the 20th century, Abhyankar is famous for one of his great contributions was in something called epimorphism theorem, where he used some kind of one of the techniques he used was a study of semigroups. And there at one place he says about his own innovation, the concept of a strict system of generators. This is something technical. Of a semigroup is a generalization of the idea of decimal expansion. This is, so I'm quoting first hand, Newton and then Abhyankar. So you see the depth of the algebra in the decimal system. Though decimal system will be placed in arithmetic. And even the word algorithm, if you look at the etymology, it has Indian origin. In this way that, as you know, the decimal system and the arithmetic based on that went from India to Arabs, and one of the Arabian expositors, which became very popular was by Al-Khwarizmi. So he explained the Indian decimal notation and the Indian procedures for the 4 fundamental operations. And through the Latin translation of his work, the Indian computation method spread to Europe. So therefore, the name for the Indian computation methods was algorithmy, which is the Latin form of Al-Khwarizmi. So that got modified to algorithmus. From there came algorithm, and from there the word algorithm. So algorithm initially meant the Indian computation method, that methods for addition, subtraction, multiplication, division, and later it was extended to any, so this characterizes the Indian methods, any well-defined step-by-step logical procedure. That means something which is computer implementable instruction. Now, a word about the Indian arithmetic algorithms for this basic algorithms. See, these are taught at a very early stage. And therefore, we tend to think of them as something trivial because, even children can learn it. One is to distinguish between the learning, which is easy and doesn't need to require any algebra, and therefore it can be taught early, and the invention. The invention needed algebraic insight. So just think of the multiplication algorithm. I have not been here very rigorous about history because the Indian method is slightly different from the way we do it now, but that difference is in that because of the writing material has changed, the principle is same. So I'm just using the familiar way of doing multiplication. So if you look at it in slow motion, what you see is that it is an application of the distributive property and the polynomial-like aspects of integers expressed in decimal system. So this multiplication algorithm itself is something highly algebraic, and that extends to, in fact, all the algorithms. And only an algebraic mind could have invented such algorithms. Then you look at the algorithm for square root. It has various rich aspects, and one of them is the formula like a plus b plus c whole square is a square plus 2ab plus b square plus 2 into a plus b c plus c square. That is implicitly involved in Aryabhata's algorithm for computing the square root. Now, look at Pingalacharya's algorithm. So, Pingalacharya's date is at least 300 BC for computing 2 to the power n. So why suddenly 2 to the power n? So as you have heard, Sanskrit chanda comprises 2 types of syllables, laghu and guru. So how many chandas of length n can be formed with laghu and guru syllables? So that's of course 2 to the power n. But how to compute it efficiently? So Pingalacharya's rules give you an efficient method of using only squaring and doubling. So let us illustrate with an example. So suppose you have 11. So if it is odd, then subtract 1. And note, so 0 here is used just as a marker. And then you get 10. So if it is even, divide by 2. And you mark this 2. So you get 5. Again it's odd. Then you subtract by 1. So you get 4. That's even. So divide by 2. You get 2. Again divide by 2. You get 1. That's odd. Subtract 1. And then you get 0. So you stop. Now, so this is the table you get, 11, 10, 5, 4, 2, 1, 0. That's what we had got. And then what you do is that you reverse the step. That you start for 0 you associate 1. And then whenever you have 1, you double. And whenever you have the label 2, you square. So you see that how you get the things back. That so corresponding to that 1, you are getting 2. Then you are squaring it. After that, you are squaring it further. So you have got 2 to the power 4. But then you are getting 0. So now don't square, you double it. So you get 2 to the power 5. And in this way, you reach 2 to the power 11. So this is a very, this is both an algorithm and an innovation. But what is behind this? And incidentally, a similar reversal occurs in Aryabhata's method for finding integer solutions of linear equations. I had thought of talking about that, but I skipped it because I realized that there won't be time. So you see, ingenious use of the exponential laws of algebra. That 2 to the power m is 2 to the power m by 2 square when m is even, and 2 to the power m is twice 2 to the power m minus 1 when m is odd. So this is, high level of algebra in 300 BC. It is not written. These rules are not written, but this it is a realization of the rules and an innovative application. So this algebra aspect cannot be, this algebra aspect should not be overlooked when discussing Pingala's innovations. And this is also an early instance of, and this divide and conquer is not, this is now pervades all modern mathematics and computer science, that you recursively break down a problem into sub-problems of the same or relative type until the sub-problems become simple enough to be solved directly. The sub-problems are then combined to produce an efficient algorithmic solution to the original problem. So the point is that there is a name to this approach, divide and conquer. The terminology may not be very aesthetic compared to the Indian terminology for these things, but there is a terminology. And you see this strategy being applied in Pingalacharya and then later again in Aryabhata's method for finding integer solutions to linear equations. So in Pingala's algorithm, you find the algebraic brilliance shining very clearly. The next, so I'll go fast on it because Manjul Bhargav has elaborated it, that how many meters of n syllables have R guru and naturally n minus R laghu syllables. So the answer is, all of you are familiar with this notation NCR. And cryptic rule in Pingalacharya displays the numerical values of NCR in the form of a table called Meru Prastar. And this, as Manjul says, in India it is known as Pascal's triangle. Now, again, there is algebra. The rule is based on the algebraic recurrence relation that n plus 1 CR is NCR plus NCR minus 1. It is not stated, but how is the table formed? It is using this, that this 4 is coming from, add up 1 and 3, 6 is coming by adding 3 and 3. So how this rule is being, applied unless you know the rule. So this algebra is there in Pingalacharya. And there are follow-ups. Varahamihir gives a twist twist in the sense that turns the Pingala's Meru Prastara and comes up with another tabular arrangement where, so I'm not, because to save time, I'm not showing Varahamir's table, but I would like to point out that that uses this Pingala's rule, or the rule underlying Pingala's innovation several times to obtain NCR is n-1 C r-1 plus n-2 C r-1, etc. And the actual formula, NCR, is the formula that is taught in permutation combination chapter in school. That is given for the first time in 17th century in the West by Heragon in 1634. But that explicitly occurs in Sridharacharya in 750. And then again in Mahaviracharya in 850. And then this is something which Manjul has already elaborated, the Virahanka sequence, which is known in India as Fibonacci sequence. So I'll skip that. No, so this is as far as some examples of arithmetical innovations which are really algebra. Then if we go back to the Vedic era, to the geometry of the Vedic era, one sees what can be called a geometric algebra. So I'll state two problems. Draw a square n times a square of side A. That means you have to construct root NA. That involves a formula. It is not stated, but one can clearly see that it involves the algebra formula n square equal to n plus 1 by 2 whole square a square minus n minus 1 by 2 square a square. And that, which one? Stated geometrically.
Sutra statement, like Pythagoras statement, Yavat Pramana. It is there. I tell you later.
Okay. So, and the n is arbitrary, and then draw a square which is equal in area to a rectangle of side A and B. That means you have to construct root AB, which involves AB equal to A plus B by 2 whole square minus A minus B by 2 whole square. So the point is that formal algebra that very clearly comes out in the time of Brahmagupta, which is early 7th century. The greatness of the Vedic mathematicians is that they were inventing mathematics algebraic in spirit and substance much before the genesis of formal algebra, and that makes them even greater as algebraists. So just to give you some example that of the constructions, so how this root n comes up. So so they are doing the ruler and compass step construction. No measurement is involved. So you form an isosceles triangle whose base is n minus 1 times a, and then you take n plus 1 a and bisect it, and that forms the slanting sides. Then they say that the altitude is root na. So here you see a demonstration of n plus 1 a by 2 whole square minus n minus 1 by 2 whole square. And similarly, how to convert rectangle. So the original rectangle is ABCD, and that is to be converted into a square. So, so this length is A and this length is B. So you bisect the remaining. So that is A minus B by 2. So the whole thing is A plus B by 2. So you draw an arc. So this length is A plus B by 2, and let it meet this thing. This part is A minus B by 2, and they say this is the required length. So they are using A plus B by 2 whole square minus A minus B by 2 whole square is AB. Now we shift to another thing. So this is here that algebra is implicit. Now let us give some examples of explicit algebra. So we come to classical algebra or high school algebra, as Abhyankar would have called it. In a personal communication, David Mumford, Fields medalist David Mumford, had told me that Brahmagupta is the key person in the creation of algebra as we know it. Because you see, you will see in literature that algebra was there in Babylonia, and then how can Brahmagupta be the creator of algebra? The issue is that what is meant by algebra. So Mumford says algebra as we know it. So let us try to define what is algebra as we know it. And Abhyankar, in his characteristic style, says, is informal says, algebra means what you do not know, call it x. The experimental data will produce an equation in x, solve it. The value of x so obtained will tell you what you wanted to know. So that's an informal way of defining algebra, and more formal way had already been defined by Datta and Singh in the preface to the History of Hindu Mathematics Volume 2. The use of symbols, letters of the alphabet to denote unknowns, and equations are the foundations of the science of algebra. And needless to say that that was a great step for rapid progress of mathematics. Now you see Brahmagupta in his magnum opus Brahmasputa Siddhanta prescribes the use of Varna. Varna has a double meaning. It means letters of alphabet as well as color. And he is using both the meanings as symbols for different unknowns. And his commentator Prithvi Goswami and others illustrate. So the first variable that already had a name from antiquity, Yavatava, that's not a color, but name was already there. So take the first letter of that, that is Ya. So Ya is X. Now rest of it you name by colors. So Kalaka, Nilaka, Pitaka, Haritaka, Lohitaka and so on. Take the first letters. So Ka, Ni, Pi, Ha, Lo. So these are the symbols for variables. And this is something which in his keynote address, Manjul Bhargava elaborated that he was, Brahmagupta, just like a modern abstract algebraist, envisaged integers as a ring. So first time that integers were presented as ring with 0 as the additive identity. Earliest use of 0 as an integer in algebra. And the laws of science are all there. And then formation of equations, that's a very important contribution in maths. There are examples already in Bakshali manuscript of equations, but it is taught in by Brahmagupta and illustrated by his commentator. So for instance, how you write an equation like 10x minus 8 equal to x square plus 1. So what they do is that there is no equality, because equality means now we think of equation as left hand side equal to right hand side, and for them it was top and below. So in the first there is no x square, so ya is, you remember, ya is x, and va is the abbreviation for varga, so square. So ya va is x square, so x square coefficient is 0, ya coefficient is 10, and ru is the abbreviation for rupa. So that denoted, rupa is something visible, so that's the constant. With 8 with a dot. Dot indicates that it's negative. And below that, you write x square plus 1. So coefficient of Yava is 1, coefficient of Ya is 0, and coefficient of Ru is 1. And now you will see that, no, but that's not an equation. Equation is written like this. But you see that what's the problem here? In fact, to clear the equation, that is to operate with equations, if it is put in a tabular form, isn't it more convenient? Then similarly, 197x minus 164y minus z equal to 6002. How will they write it? Let's just look at the first one. So here there are x, y, z. So for that you have ya, ka and ni. So that's 197, 1644 with a dot and 1 with a dot. And there is no constant on the left hand side, so Ru is 0. And on the right hand side, this 6002, it comes with Ru, and the others, I mean, there is no variable there. So Ya, Ka, Ni, they are all 0. So this is how the equations were explicitly framed. Then the algebra of polynomials. What? Polynomials and power series, may they ever rule the world. Brahmagupta teaches how to add, subtract and multiply polynomials in several variables. And his statement is as modern as it can be. Add and subtract squares, cubes, 4th powers, 5th powers, 6th powers, etc. of the same variable. That means 5x square plus 6x square is 11x square, 2y cube plus 7y cube is 9y cube, etc. And leave others. That is, what is 5x square plus 2x cube? Just leave it as it is. The product of the two unlike unknowns, product of two like unknowns is a square. So x into x is x square. Whereas the product of 3 will be or more will be like, y, so that's y to the power 5. And product of different unknowns, just leave it as it is. And that was called bhavitaka. And operations are done on them as before, as you do with the like terms. So in retrospect, Brahmagupta defined not only integers as rings, but he also gave the structure of polynomial ring in several variables in this verse. Quadratic equations. It is actually known to Aryabhata, but he didn't state it in full generality. He stated in a context where A, B, C are quantities in problems on arithmetic mean or problems in interest. And Brahmagupta first describes it algebraically. That is, he describes the formula out of context for arbitrary ABC. And it is very significant that what is his term for quadratic equations? Madhya harana. That means elimination of the middle. And by the way, in that same poem of Abhyankar, Polynomials and Power Series, there is a term, eliminate, eliminate, eliminate. Because, there was a tendency in modern algebraic geometry to remove elimination theory. And now elimination theory has made a big comeback in modern algebra. So Abhyankar had said, eliminate, 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 eliminate the eliminators of elimination theory. And so here you see, Brahmagupta says the first part, eliminate, eliminate, eliminate.
What is the word, Sanskrit word for eliminate?
Harana, harana. Madhyam. Okay, so elimination of the thing is that the trick to solve ax squared plus bx plus c, that is, you have to eliminate b. But how to eliminate by b? That obviously Brahmagupta knew that by completing the square, but he didn't spell it out. He just gave the formula. And Sridharacharya apparently spelled it out, but his treatise is lost, but is quoted by Bhaskaracharya. So we call it Sridharacharya's formula of completing the square. And thanks to the use of negative numbers, Indians gave a unified treatment of quadratic equations. And in Arabia and Europe, they used to consider the different cases separately because for them ABC were always positive. And again, it's profound, this idea of Madhyaharana or completing the square, it is so profound that when Abhyankar is writing a review article on resolution of singularities, that's one of his claims to fame, that his guide Zariski had solved the problem in special case, and then Hironaka had proved it in full generality in characteristic 0, and Abhyankar proved some difficult cases in characteristic P, positive characteristics. So the killing of B1 was the basic trick underlying Zariski's and Hironaka's proofs of resolution of singularities of algebraic varieties of 0 characteristics. You just see that how much reverence is showing for this idea of completing the square, so much so that there is a theorem of Newton for which Abhyankar gave a proof. It's Abhyankar's proof. But Abhyankar doesn't call it my proof, he calls it Sridharacharya's proof, because the underlying idea is that completing the square. Now, a quick thing that that Indians, just not quadratic equations in one variables, they also solved simultaneous quadratic equations with effective applications in commercial arithmetic and astronomy, simultaneous linear equations in several unknowns. Again, method of elimination, Gaussian method of elimination that occurs in Brahmagupta. And this is an unfortunate thing because I would not be talking about this because this is very relevant to today's topic. The integer solutions of linear equations and equivalent problem of solving the problem of simultaneous remainders, which is known as Chinese remainder. So all this thing occurs in Aryabhata. And this is now fundamental in cryptography. And incidentally, this was initiated in Europe by Bachet in 1621, and Bachet's work inspired Fermat in his to come up with his principle of descent. And then there, yeah.
Jordan of memory, he also has the Pascal triangle.
Oh, okay, okay.
Triangle known as Pascal triangle in
Yes.
India. Jordan memory.
And then there is this very thrilling story of integer solutions of nx square plus 1 equal to y square, where n is non-square positive. And this is very important in modern algebra and number theory. And one of the applications in ancient time was to find a method of generating progressively better approximations of root n. Because if you find integer solutions x and y, then that your y by x gives a very good approximation to root n. And if you have a way of generating larger and larger solutions, you will get better and better approximations. So this was initiated by Brahmagupta, and complete solution, and he gave a composition law, which I am going to talk about after this. And complete solution was given by Jayadev, Bhaskaracharya, and Narayana, again using Brahmagupta's composition law. And to see the intricacy of the problem, just look at the problem of solving 61x square plus 1 equal to y square. See the smallest positive integer solution, how big they are. And this occurs in Bhaskaracharya. Then Farma again states the problem of Brahmagupta as a challenge in 1657, and he also includes Bhaskaracharya's 61. And Andrevel makes this interesting statement about Farma's challenge. What would have been Farma's astonishment if some missionary just back from India had told him that his problem had been successfully tackled there by native mathematicians almost 6 centuries earlier. One thing to be noted here is that Brahmagupta was the first to write a separate chapter on algebra. And at the beginning, algebra is presented as a distinct, powerful, indispensable branch of mathematics. The core topics of algebra were listed: symbols, operations with 0, negative and positive numbers, and various types of equations. And the indispensability and power of the subject was emphasized both at the beginning and at the end of the text. And the importance of algebra was, which Brahmagupta emphasized, that was further reinforced by Bhaskaracharya in his book Bij Ganita. And see how charming his description is. Charming for mathematicians and astronomers, easily accessible to youngsters, algebra, the essence of mathematics, is demonstrated here with examples. It is replete with excellence and devoid of defects. Pada, learn it for acquiring wisdom and confidence. And this again reminds me of Abhyankar, that devoid of defects, that Bhaskaracharya is saying that algebra is devoid of defects, because somewhere or the other in science there are kind of somewhere some informality, some gaps come in. Once, this was in Bombay IIT, somebody was telling Abhyankar, one of his former students, that his theorem, epimorphism theorem, has, somebody has given a topological proof. And then he says that, an alleged proof. So Abhyankar says, why say alleged? Why make that insinuation? A topological proof may well be 99% correct. See, as long as you do not algebraicize it, I will not give it 100%. So with that you can appreciate Bhaskaracharya's statement, devoid of defects. That 100%, Abhyankar's 100%. Just a quick thing, that series, all arithmetic series, the results you know, and things which are not even done in school, this occurs in Aryabhata, and in Sridharacharya you have I mentioned Mahavira, but Sridharacharya also has it, the geometric results on geometric progression. There are miscellaneous results on binomial surds in Brahmagupta, that formula for root of a plus root b. And there are several formulae on permutation and combinations in Indian texts. Bhaskaracharya takes the bold step of introducing infinity in mathematics and defines rules of interactions with usual numbers, like infinity plus x is infinity and infinity minus x is infinity. And the idea of adjunction of infinity has now been put on a very firm footing in branches of higher mathematics. Now I come to the third phase, that what I would call anticipation of modern abstract algebra in Brahmagupta. So Brahmagupta is not only the founder of classical algebra, he also introduced the principle of composition, which is the quintessence of modern abstract algebra. So composition basically means that you combine two mathematical objects of a certain type to produce a third object of the same type. For instance, compose two solutions of a given equations to produce a third solution of the same equation. So now you see that, look at that problem, nx square plus 1 equal to y square. So what Brahmagupta says, if x1, y1, z1 and x2, y2, z2 satisfy it, then so does x1, y2 plus x2, y1, nx1, x2 plus y1, y2 and z1, z2. More than that, what is said in India is that it is called a binary operation with a name for it, bhavna. Bhavna means in Indian mathematics composition, like sine of a plus b is sine a cos b plus cos a sin b. That rule is also called bhavna. Bhavna means composition. So this is presented as composition on the solution space of nx square plus z equal to y square. And this sophisticated idea of constructing suitable composition laws on abstractly defined unknown elements is a central theme in modern mathematics research, not just study. I'm emphasizing the word research. And this is perhaps the greatest single original idea in the vast grand spectrum of ancient Indian mathematics. By that, what I mean is that, other great things like decimal system, that comes as an evolution. I mean, you have this oral vocabulary in the Vedic thing, then somewhere notation comes up. Calculus in Kerala, these are great contributions, but you can see that there are preceding ideas, that this comes as an evolution. But here, this comes like a magic. There is nothing preceding Brahmagupta's work which suggests that how this could have come. It is something which only one can think of Ramanujan, that when he came up with something, it just, people have no explanation that, this cannot be explained by the evolution of mathematics. So composition law has that status. And just to give you an idea that where it lies in modern, in modern study of mathematics. So in high school, one studies what is called classical algebra. Then when one goes to college, modern algebra starts. So first students study groups, rings as abstract structures. Let us say at the BSc. At a higher level, one learns to study associating abstract structures to mathematical objects. Like, for example, to a polynomial, you associate a certain group. At a third level, that is after MSc, only very specialized researchers in algebra or number theory, not all mathematicians, they do this work of constructing binary composition on important sets. This is a research topic. For example, I would have heard of elliptic curves. It is very central to frontiers of mathematics now. So there is so elliptic curve is a geometric object, but there an addition law is defined. With these 2 points, you associate a third point which satisfies certain group laws. So what as Brahmagupta did, he created one, that is algebra of the high school, and the same person he sold to the top layer of the second. That is this constructing binary composition, which comes, even in modern times when a student studies, he doesn't study these things, constructing binary composition. He looks at natural compositions. And just to give you an idea, that new horizons were opened by Brahmagupta's composition law when it reappeared in Europe. So let me skip things and just let me tell you that one of Gauss's, let us just come to the end of this page, one of Gauss's deepest discoveries was composition of binary quadratic forms. Brahmagupta's case was a special case of that. So Brahmagupta's rule can be thought of as composition of binary quadratic forms of the form y square minus nx square. And Gauss does it in full generality, that is ax square plus bxy plus cy square. And Manjul Bhargav, who is in the audience, he shot to fame by coming up with higher composition laws, simplifying and generalizing Gauss's theory. So you can see that where Brahmagupta's work stands. And just to give you a picture, this is not a book in history of mathematics. This is very specialized research monograph of Manuel Ohangaren in 1990, titled "The Wheat Group and Problem of Luroth." And you see, you see the item 5, that is also Sprag Brahmagupta. Also Sprag Brahmagupta. So this Brahmagupta's composition law, his original verses, it starts with that. Why? Because the first result in this chapter is a restatement of Brahmagupta's law. And the second chapter is due to Pfister. Second result is due to Pfister. And Pfister's result, Pfister gave his result in 1965. And this is 628. So again, you can see that where it lies. Let me skip this. So I had written an article on the Brahmagupta's this composition law, and when Mumford saw it, he wrote a letter to the editor of the Bhavna. So he again repeats that Brahmagupta was the real inventor of algebra, and then he again agrees the law of composition with Pell's equation is true algebra, a clear glimpse of modern abstract algebra, and abstract he puts in inverted comma. Now, just I began with this introduction about why I insisted on the title Algebraic Insights, because there are these pitfalls of labels. We tend to give some label to a work of mathematics and then get attached to that label. So and these labels have some antagonistic nuances. So for instance, this applied or practical mathematics versus pure mathematics, or algorithmic mathematics versus abstract mathematics. So there is this feeling that Indian mathematics is, and this is emphasized by several authors, that applied or practical, whereas Greek is, pure and abstract. So sometimes what happens is that Indian authors, they tend to, what they say is that Greek mathematics is ivory tower mathematics, and we did real practical mathematics, algorithmic mathematics. It is as if, pure mathematics is something, this is for, wealthy people and with no, not for practical application. The outcome of that, this, overemphasizing that Indian maths is applied and it is algorithmic, is that great achievements which do not conform to such broad labels get neglected or denied. Because when I'm saying that Indian maths is algorithmic, or Indian maths is, computational, or it is, practical, then something which doesn't fit my thesis, I would not be, putting it, because it would not be relevant. What is the outcome of that? Van der Waerden, who is, serious historian of mathematics, he writes that about the Indian works on Pell's equation, including Brahmagupta's work, that this must have been done earlier by the Greeks, although there is no evidence anywhere. But the fact that it occurs in India is reason for him to speculate that it was in Greece earlier. And Brahmagupta and others copied from Greek sources. He uses the word copied. The argument he gives is that Brahmagupta was an astronomer. Why would he be interested in Pell's equation? Now, this is because of, our emphasizing that, the abstract mathematics is something Greek. We don't do that.
Not our, their emphasis.
Which one?
It is because of their emphasis.
But Indians also said that Indian mathematics was utilitarian. Yeah, okay, Indians repeated. Okay. So, even this algorithmic. So when we say Indian maths is algorithm, therefore you emphasize on Kutaka and Chakrawala, and you neglect the underlying principles there, like this this principle of descent which is there, or the greater thing that Brahmagupta's Bhavna. In fact, when I was first invited to give a talk in CMI, I was told to lecture on Kutaka and Chakrawala, and I put Bhavna in between. So, and then again, mathematicians, they sometimes spoil a work. So in Brahmagupta's work, they realize that it is a multiplicative of norm function and emphasize that. So which makes it an important identity. But then it gets lost that it was a law of composition, which is much more fundamental than just, one among many identities. So you see that this bhavna defies simplistic labels. It manifests the fundamental principle of modern abstract algebra, but does so in the language and framework of classical algebra. You don't have the, before Brahmagupta writes, there is no definition of groups, rings, fields. It's written in classical style, but it demonstrates the essence of modern abstract algebra. Again, this algorithmic versus abstract. Where does bhavna arise? It arises out of algorithmic mathematics to give an algorithm for solving the Brahmagupta-Pale equation. But it leads to, and it also leads to the discovery of the final Jayadev Bhaskara solution. So the bhavna led to the discovery of the astonishing algorithm. So this abstract bhavna that arose out of algorithm, and it was responsible for the algorithm also, responsible for the invention of the algorithm. And yet it stands apart as a result whose significance far exceeds that of the original problem. So to conclude, this computational or algorithmic approach and the conceptual abstract approach is inseparably fused in this work. So when I had got the invitation to talk on computations, algorithms and innovations, etc., what came to my mind was a Bengali kirtan. Kirtan, is a hymn to Krishna. So it goes like this. Aki ange eto rupo nayone na dhare. So Aki is in a single. Ango is body. In a single body. So many forms, so much beauty. My eyes can hardly behold. This is the devotee is saying about Krishna. And when you look at Indian maths, the same thing comes up, that my eyes are totally dazzled by so many forms of such beauty in a single frame. That you look at this piece of work in ancient Indian mathematics, it dazzles by its many splendored beauty in a single frame. Algorithmic aspect, computational aspect, innovative aspect, combinatorial aspect, algebraic aspect, all this many splendored in single piece. And it just reminds one of that kirtan. References. The best reference for Indian algebra is the History of Hindu Mathematics by Datta and Singh. But you have to remember that Datta and Singh wrote at a time when modern algebra had not come out in the curriculum. So Vibhutibhushan Datta was an applied mathematician. So these things were not emphasized, the modern abstract algebra aspect.
Even Van der Waerden's book was not out.
Van der Waerden wrote in 1930. That's the first book on modern algebra in 1930. And Datta wrote his papers in the 20s and the book in the 30s. So I have written on these things, like for example, the Bhavna in Mathematics, which was the first article in the first edition of Bhavna. And in fact, it was at the request of Manjul or suggestion of Manjul that I had written this article, Bhavna in Mathematics, which traced the history of composition laws from Brahmagupta to Bhargav. And then the Kutaka, which I didn't talk about because I knew I would run out of time, that is elaborated in part 5, that is in January 2023, and about the foundation of algebra in April 2023, and the Bhavna itself is elaborated in these two issues, October 2023 and January 2025. And there is a separate article on today's theme, Algebraic Insights in Indian Algorithms, in a book edited by Gopinath and Sharma. So, thank you.
Thank you, sir, for bringing out all the dimensions of the Indian imagination. We now have Professor Aditya Kolachana, who is at the Department of Humanities and Social Sciences at IIT Madras and works on the history of science in India and manuscriptology. He heads the Center for Indian Knowledge Systems at IIT Madras, and he's a recipient of the Best Teacher Award at IIT Madras, as well as the Young Historian of Science Award from the Indian National Science Academy. He'll be talking about practical problems discussed in Indian mathematical works.
Take out. Okay, good afternoon everyone. So I know we've just had a discussion on how Indian mathematics is not simply practical and it has a lot of abstract stuff too, but this was my topic to to talk on the practical problems in Indian mathematics. So I thought about what all to talk about in this in the given limited time. So when I thought about it chronologically, I thought what are the critical problems which were dealt with, and so these are a few problems, time permitting, I'll be discussing. The practical application of the place value system, determining east, it's as practical as it gets. Application of Kuttaka in astronomy. So this Kuttaka has been dealt already by a couple of speakers, but we don't find too many discussions on its exact applications in astronomy. There is an interesting problem given by Ganesha Devagnya, so we will just look at how it is actually applied in astronomy. Already the Varga Prakriti has also been dealt with somewhat, and its application in the determination of square roots. We'll maybe have a quick look at that. Combinatorics has been dealt with extensively. Perhaps one new Meru which has been discovered by my student and me recently, I'll just briefly present on that. And then some of the more general problems in Bhaskara's Leelavati. So, practical considerations also contributed to the development of mathematics in India. Particularly requirements in a variety of fields. So philosophy influenced the conception of zero and infinity. Commerce and trade contributed to the prevalence of the decimal place value system. Construction of fire altars led to the development of geometry. Prosody and music required the evolution of combinatorics. Astronomical timekeeping and planetary computations demanded the progress of trigonometry, algebra, mathematical analysis. So we find a variety of practical problems pertaining to almost this whole variety of fields in Indian mathematical and astronomical, musical, prosody texts, etc. So let's quickly have a look. So we know that most Indian mathematical texts actually start with the definition of the place values. Aryabhata does it, Leelavati does it. And what is the practical application? The commentator Bhaskara replies. What is the potential of this place values? It's very interesting. He says, Krayakaha Vishesheshta Kriyabhajanaha Syuhu. This is for, it's easy for traders to tag prices to their commodities. So the practical application of the use of place value system, it's been defined by the commentator of Aryabhata, Bhaskara, as its applications in trade and commerce. One of the fundamental problems in astronomy was determining east, because you needed to, determining east is critical for all construction activities, particularly if you want to have a well-designed, well-ventilated, well-lit house. And it also had applications in the Vedic rituals. So determining east was a very, very critical aspect of the culture, and determining east is a actually a mathematical problem in some sense, because you need to understand the spherical trigonometry, and that will help you solve this problem. In fact, I won't get into it, but several commentators, commentators also ask the question, why can't we determine east by just looking at the sun? And then they say that that's because the sun doesn't rise in the same spot throughout the year. It has the motion, northward and southward motion over the course of the year. So you can't determine east just by looking at the sun. But the problem remains. Assume you go to a new place. You can't say wait for the equinoctial day to determine what is the perfect east. So you need to be able to solve it at any given place at any given time. And so as far back as in the Shulba Sutras, this problem is addressed and solved. So this is the sutra, Same Shankhum Nikhayas, Shankhu Sammitaya Rajva Mandalam Parilikhya, Yatra Lekhayoho Shankhagrachaya Nipatati, Tatra Shankhu Nihanti Sa Prachi. So you place this Shankhu, the gnomon, and you draw a large circle around it. And then twice in the day, once in the forenoon and once in the afternoon, the tip of the shadow will fall exactly on the circle. And the solution is you join those 2 points, that will give you east-west. The sutra is only this much, it doesn't get into the math of it. But if we go into the spherical trigonometry, we will understand that the sun's diurnal path will be parallel to the celestial equator. And so when you, what you are achieving by drawing the circle and measuring the shadow, effectively you are measuring 2 times in the day when the shadow lengths are equal. This is ensuring that you are finding 2 times in the day when the sun's altitude is equal. And so on the diurnal circle, when the sun is at equal altitude in the forenoon and the afternoon, and you join that line, that will be parallel to the east-west. So that's the mathematical rationale here. They were also aware that because the sun's declination changes over the course of the day, this will not give you exact east-west. Actually, there will be a small error associated with it. And several astronomers, mathematicians have given the solution to correct for this error as well. I think the earliest known solution for this is in Prithutaga's commentary of Brahmagupta, where he explains how to correct for the error in the east-west computation using this method. Later on, I think Bhaskara has given it in Siddhanta Shiromani, and then Nilakantha has given it in Tantra Sangraha. So the formula is here. This is the formula given by Nilakantha in Tantra Sangraha. Bhedat purva parakrantyoho chaya karnangala hatat lambagaptam purva bindoho nitva karyotra soyanat. So there is a very interesting math associated with this, how you actually compute the error, and what will be the, so W prime E prime and W prime E double prime will give you the difference between the computed east-west and the using this method, using the Shulba Sutra method, and then how you actually, this will allow you to, this difference between E prime and E double prime is the error, and that is caused due to a difference in the declination of the sun over the course of the day. And so you can see that the formula, the correction formula, is a function of the declination of the sun in the forenoon and in the afternoon. So this is a very, very interesting practical application of mathematics in solving a very, very fundamental problem essential to astronomy as well as general human life. Application of Kuttaka in astronomy. So we have seen enough about Kuttaka. These are equations, first order indeterminate equations of the type Ax plus minus C equals By. And generally we hear that why these problems needed to be solved was because it has applications in astronomy, but generally we don't read where exactly the application lies. This has been first discussed by Aryabhata, but Bhaskaracharya does a much more extensive discussion of this in the Leelavati. And in the commentary of the Leelavati, Ganesha Devagnya actually presents a particular problem where he showcases its application in astronomy. So consider a hypothetical celestial body which completes 10 revolutions. I am paraphrasing here. 10 revolutions in 19 days. This is the problem. And so what would be the position after 12 days? You can simply compute 12 times 10 by 19 will give you 6 by 19 revolutions. which if you expand, it can be written as 6 revolutions, 3 rashis, 23 degrees, 41 minutes, 3 by 19 seconds. So now the question comes, I used to, when I was in school, there used to be these kind of problems that there is something, then someone carelessly erases the board. And so now you need to reconstruct the problem in reverse. So this is almost like that. So now the question is, given only the fractional portion of seconds, only this partial data, can you reconstruct the entire position of the planet? And when we think about it, what is this? How does this apply in astronomy? You may be able to see the position of a particular planet on a given day at a given instant, and say you have some data, and can you compute its ahargana in how many days in its revolution have been elapsed? I think that's the sense of the application which comes here. So the question, when I first encountered this problem, I was like, but this 3 by 19 will occur like several times in a revolution. How can you even solve this problem? And that's where the beauty of Kuttaka comes in, because you fix the condition that the ahargana has to be an integral value. And once you put that condition, there can only be a unique solution within the kalpa. I mean, if you go to a second kalpa, there will be another solution, but within that kalpa of 19 days, there will be a unique solution. And so this is, you have to frame the Kuttakas, and so you'll have to frame 5 Kuttakas, and then you can compute the integral value of minutes, the integral value of seconds, minutes, degrees, rashis, revolutions, and the ahargana itself. You can, by framing a series of Kuttakas, this problem can be solved in reverse. And this is what Ganesha Devagnya shows to be the, so for instance, you know that the number of seconds is 3 by 19. So how do you find that the integral value of seconds and the fractional value of minutes? So it's very simple. You know that because the denominator is 19 here, some x by 19 times 60 will give you y plus 3 by 19. That's the Kuttaka. So this is the Kuttaka. X by 19 times 60 will give you y plus 3 by 19. This is a Kuttaka problem. You solve for this, and these Kuttaka solutions also give the least positive integral solution. So that's why that's another reason why Kuttaka is required to solve this problem in reverse, because you need the least positive integral solution. Only that will give you, because when you say you do 60 by 19, this 3 will give you the smallest the quotient possible, integral quotient. And so you can by framing a series of Kuttakas, you can solve in reverse you can go from second to minute. So the same Kuttaka which we framed here, 60x minus 3 equals 19y. By solving for this, you will get the integral value is 3 seconds, and then the remainder of the higher unit, which is minutes, is 1. So 1 by 19. So basically you get this 3 seconds and 1 by 19. And so now you frame a Kuttaka again to convert from minutes to degrees. And so you will get another Kuttaka, 60x minus 1 equals 19y. And so you will get that the number of integral value of minutes is 41, and then the fraction of degrees is 13. And ultimately, by solving it this way, you will get the ahargana in reverse. You can compute that it is 12 days. So this is how it is shown by the commentator explains the application of Kuttaka in astronomy. I will move on. Varga Prakriti, this has been dealt with. So these are problems of this nature, x square minus dy square equals k. And one of the interesting applications, this also has applications in astronomy. In fact, I think Brahmagupta presents a problem in the Brahmasputa Siddhanta where you need to solve. I mean, in the Kuttaka Adhyaya, there are several problems which are basically astronomical problems. But I thought rather than focus on those problems, I personally really enjoy using it as a method of finding rational approximations for square roots. So the problem which Professor Datta hinted, this is the verse of Bhaskara's in Bija Ganita, where he poses two problems. X square minus 67y square equals 1, x square minus 61y square equals 1. There is the Chakravala solution, But if we were to look at how the rational approximations work, if we consider x square minus 2y square equals 1, we can see that each successive solution gives a closer and closer approximation of root 2. So the first solution can be, this is a simple problem. You can see by inspection, 3 and 2 is the first solution. It gives the first approximation to root 2 as 1.5. The second solution is 1712, and this gives the second approximation as 1.416. The third solution is 577 and 408, which gives a very good approximation of root 2, 1.414. This is the Shulba approximation. This is the remarkable thing. I don't know if the Shulbakaras were using Varga Prakruti, perhaps not, but it's definitely interesting that the Shulba Sutra approximation to root 2 is actually the solution to the Varga Prakriti equation. By the way, even the second solution is what Nilakanta hints at. In his Aryabhatiya Bhashya, there is a passage where he talks about how Bodhayana would have arrived at the approximation of root 2 as 577 by 408. And he starts by saying, assume 2 squares of side 12 each. And, that will be one, their sum will be 1 less than a square of side 17. And then he kind of says, Spashtam kind of, it's like, therefore, hence proved, he concludes his argument. So that's.
Also mentions 17 by 12.
17 by 12, correct. So,
1 plus 1 by 3 plus.
Correct. So, so this is one interesting application I thought of Varga Prakruti in addition to the astronomy. If we move on to the combinatorial problems, again several such problems have been discussed. Chanda Shastra, the Meru Prastara has been discussed. I will not get into it. The Viryahanka sequence has been discussed. One thing which has not been discussed is the Khanda Meru, which is also very, very interesting. So the Khanda Meru, it is found in the Sangeeta Ratnakara of Sharangadeva. And so when you have 7 musical notes and you combine them, so they have a way of systematically enumerating all the possible combinations. And they also have this Nashta Uddishta problems, where given a row number, you want to know the pattern in it, and given the pattern, you want to know the row number in it. So we have Professor M.D. Srinivas here. He and Professor R. Sridharan and Raja Sridharan have written a very interesting paper on this, that the underlying property here is actually that any integer can be represented as a sum of factorials. And that property can help solve this. And this Khanda Meru is actually a tool which simplifies that the process of expressing as any integer as a sum of factorials. And both the Nashta and Uddishta problems make use of that property. So this is I would say like a practical application in music of combinatorics. I would briefly talk about one new Meru which we published a paper last year on, called the Sanyoga Meru. This is also found in the Sangeeta Ratnakara. Actually there is still a fair bit of mathematical combinatorics in Sangeeta Ratnakara, which is not yet, I believe someone at IIT Bombay is doing a PhD on it. I don't know where it has progressed. But just to explain this Meru quickly, in music, there is this concept of tala. Tala is a unit of musical time, and it consists of subunits called talangas. And Sharangadeva defines 4 subunits called Dhruta, Laghu, Guru and Pluta. And these are in the ratio 1:2:4:6. And you can combine these to arrive at any given n. Suppose you want a duration of 10. What are the all possible ways that you can combine these talangas to arrive at a duration of 10. So mathematically speaking, this is basically partitions. And so for instance, you want a duration 8. There will be 60 possible ways in which you can arrive at a duration of 8. So this table shows you that. So L is 2 and P is 6. So 1:2:4:6. Dhruta, Laghu, Guru, Pluta. So 2 plus 6 is 8. DDP, 1 plus 1 plus 6 is 8. They have a very systematic enumeration of this as well, how you go about it. And the underlying property of this, as Professor Srinivas and others have shown, is that each integer here is expressed as a sum of the Sharangadeva sequence. So that's a very interesting property here. So now the question arises, similar to the Lagakriya question which gives rise to the Meru Prasthara, the question arises, can you tell me how many number of talas have a given number of laghus, or a given number of dhrutas, or a given number of laghu and dhrutas, or a given number of dhruta and plutas? So this is the kind of question which arises, and the answer to that is what is called the Sanyoga Meru. This is what's given here. So you can see this n here is the duration of the tala. N is the duration of the tala, and it shows how you can combine the different talangas to arrive at that n. So for instance, let us take 8, because this was the table we were showing, n equals 8. What this table is telling us is that there is one tala of duration 8 having only dhrutas, one having only laghus, one having only gurus, none having only plutas. That's obvious because pluta is 6, so you can't add 6 to arrive at 8. There are 32 talas with a combination of dhrutas and laghus, 5 with a combination of dhrutas and gurus, and so on, 12 with a combination of dhruta, laghu and guru. And their total sum is 60. And the sums that you see here, this is the Sharangadeva sequence. The Sharangadeva sequence being each number in this sequence for n greater than 4 will be n minus 1 plus n minus 2 plus n minus 4 plus n minus 6. This is the Sharangadeva sequence. And in effect, what this number is telling us, this is telling us all the ways in which you can add up to 60. Okay, this is the partition theory. You can add up to 60 through the unique sums of unique integers, unique numbers. So you can arrive at 60 by, not at 60, you can arrive at 8 through a unique combination of ones. You can do it by 8 ones, you can do it by 2 fours, you can do it by 4 twos, and so on. So this is so this Sanyoga Meru is showing how we can solve this problem of determining how many talas have a given number of talangas in any possible combination. It's a very interesting mathematical problem. This has been in about 18 to about 19 verses. It has been addressed in the Sangeeta Ratnakara. I will conclude with some few interesting problems in Leelavati, some more mundane day-to-day problems which are discussed in the Leelavati. Some of these will be quite popular. There is, of course, the basic computation of interest, and there are fairly sophisticated problems even in interest computations. So the principal has been given out in 3 parts with different interest rates. Okay, and you are told that the interest that you obtain on all three parts of the principal are equal in different number of months, in 7, 10 and 5 months respectively. And so you need to tell in what proportion the principal amount was distributed separately. So this is a interesting problem in computation of interest. So this shows application of math in trade, commerce, finance, etc. There is a problem in the sharing of profits. So there are partners in a business, and they have like a share of the business each, and that has resulted in some profit, and the total principal plus profit is stated, and so now we have to compute what will be the profit share of each of the partners in the business. So an interesting problem in the Leelavati. So several of these problems, there is an entire chapter. The chapter itself is interesting. It's called Mishra Vyavahara. So it is problems with mixtures. So it's interesting how these things are viewed, right? So computation of interest is viewed as a problem of mixture because the principal plus interest is considered the mixture. Similarly, you invest money in a business, the capital plus profit, the resulting profit and the capital is viewed as a mixture. Or for instance, there is this famous problem of the filling of a pond. There are several streams which are flowing into a pond, and each, you are given the time in which each can individually fill the pond. And so then you have to tell the time in which they combinedly fill the pond. So again, a problem, this is considered, several streams are mixing in the pond. It's a problem in mixtures. There is the problem of purity of gold, again considered a problem of mixtures, because you have gold nuggets of different purities and then they are being all molten into a single nugget. And so now you need to tell what is the purity of the resulting nugget. Very, very interesting. The problem in carpentry. Okay, so this has been dealt even by Brahmagupta. This actually is, I find it very interesting that such problems are dealt with in mathematical texts. I think the fundamental issue here was, how do you determine a carpenter's wages? So carpenter does some work, how do you determine their wages? And so they figure that it is a function of, one, the cross section of the wood that you cut, which makes sense, right? If the cross section is small, then obviously there's not so much effort involved. If the cross section is large, greater effort is involved. And the second function is, it's a function of the hardness of wood. And and this is, so in effect, you're solving a problem in geometry to determine the carpenter's wages. And so we find such problems in Brahmasputa Siddhanta as well as Leelavati.
And there is a separate name for it, the section.
Krakacha Vyavahara. It's a separate, whole separate chapter, yeah. With a title that indicates, the significance, the importance of this chapter. Similarly, you have problems in agriculture. I think in those days they didn't have this large weighing scales or whatnot. They needed a quick fix way of determining the quantity of grain which has been produced. And so the standard practice was to heap the grain once you harvest it on the edge of your field or wherever. And so there are problems which tell you so Bhaskara gives rules to determine, and they recognize the fact that different grains will heap differently given their structure. So large grains will heap differently, small grains will heap differently, pointed grains will heap. And so there are different rules of thumb to quickly determine, based on the dimensions of the heap, what is the quantity of grain which is up for sale. So this is quite remarkable. And all this clearly indicates, there is, among some, there is a misconception that math was an elite discipline only meant for certain sections of society. Yeah. But this clearly indicates they were targeting and different sections of the society and trying to deal with problems which will be felt with all sections, dealt with people from all sections of society. So this is, I think, very, very interesting insight that and what is the point of discussing these problems if the farmer or the carpenter is not studying this? I don't see any point in them putting these texts. I don't know if they were studying it directly from the Sanskrit or these were being translated into the local bhasha. That's a different thing. But clearly this is meant to be studied by people from different sections of the society. So I will just conclude that Indian mathematical texts have dealt with problems in several major areas of human endeavor. And its prevalence, the prevalence of mathematics in specialized texts such as in prosody, music, medicine, I have not discussed, but there are combinatorial problems in medicine as well. They reveal, I think, very significant clues about the culture and pedagogy of mathematics in India. Firstly, it's clear that these people were not, they didn't specialize in just one field. They had some interdisciplinary skills. There is no way a Pingala or a Sharangadeva were doing such sophisticated math without the study of math. And what does this secondly imply to us? It implies to us that people from a wide cross section of society were studying math. For instance, in one of the commentators of Sangeeta Ratnakara, Sharangadeva, Sharangadeva's Sangeeta Ratnakara is Simhabhupal. Simhabhupala. Simhabhupala in fact states that he belongs to the Shudra caste, and then he gives a he has written a complete commentary in Sanskrit, and then he proudly proclaims, he states that I come from the feet of Vishnu, from which the Ganga also flows. So he claims his kinship with Ganga, and so this shows that math, it was not as elitist as we think it to be, and there seems to be a fairly so it was not confined to an isolated elite, but practiced and applied widely by scholars from a variety of backgrounds. Also, it need not be said that also of note is the compelling poetic pedagogy and use of imaginative examples, which make math much more approachable, accessible to the general public, and all modern teachers would do well to take inspiration from this. Thank you.
Also, this excavation problem.
Excavation.
Along the lines of carpentry and this.
Yes.
Same way.
Correct. Excavation and Chiti Vyavahara also. I didn't put all those. Chiti Vyavahara is also there. The construction of the altars, all complex altars with different brick shapes and whatnot. Yeah.
All these verses that you quoted,
Huh.
are they all from Leelavati or from different sources?
Only that last section was from Leelavati. The previous ones were from other texts, Aryabhatiya, Bijaganita.
I mean, about the agriculture, about
Those all were from Leelavati, but we find some similar such verses even in Brahmagupta. Yeah.
Thank you. There was so much to say in this session, so I'll request Professor Srinivas to honor Professor Dattu and Dr. Professor Kolachana. So we have a 20-minute tea break, and then we'll reconvene for the lecture demonstration, the Sarangi and vocal.
that's here.
Yes, here. We'll reconvene here at 4 o'clock.